Hello, everyone. Thank you for attending the Query Planner for GraphQL talk. My name is Kesler, and I've been working with GraphQL since the spec was out in 2015. I have contributed to the with the critical performance improvements and algorithms to the GraphQL Java project. My team and I, we've been working on the project with the goal to automate orchestration over a large set of the capability services across the company. We had design discussions also with the GraphQL Java folks with respect to the query analysis and query planning capabilities. And my team is currently working on implementing Query Planner for GraphQL Java that we plan to open source hopefully in March next year. And in this talk, I will share some of the ideas that we are building into the query plan for GraphQL. So this is the agenda. We will look at the standard GraphQL query execution. Then we will introduce the query plan. We'll discuss the key query analysis components that need to be built into the query plan. We will see how query plan simplifies query cost analysis. And finally, we will discuss other two cool capabilities provided by the query plan beyond GraphQL spec. In order to start looking into the examples, I would like to introduce or imaginary schema that we will build the examples, GraphQL examples around for. Imagine that we have a pet store or pet club where we can keep the animals. Each animal has a name. Each animal can have friends. It can and we have the three concrete animal types: dog, cat, and bird. All of them implement the animal interface. Also, we can have the special union type pet, which combines dogs and cats just for demonstration purposes. But again, this is imaginary schema that will help me to walk you through the examples. And also, finally, we have the type friend that is that also has names. It could have the certain attributes and also the list of pets that this friend is friend with. So let's assume that we have a query that queries for one single animal. We specify the name of the animal in the argument for the animal field, and we are asking for the bunch of fields of the animal. And in case the returned animal is a dog, we want the dog specific fields. In case the animal is a cat, we want the cat specific fields. In case the bird, we want the bird specific fields, and also we want to query for the friends for that animal. So let's look how the standard query execution goes. So the execution begins from collecting the fields in the topmost selection set. In our case, the topmost selection set is the selection under the query under the query element of the query, and we have one field to collect, which is animal. So imagine that we have collected that animal field. Now we need to resolve that field. The GraphQL engine goes ahead and invokes the animal field resolver, and animal field resolver queries the animal's data source, and animal data source finds the animal with the name Toby and sends the response back to the server. In our case, this is the dog. The next step in the query execution will be to collect the fields in the animal selection set, and there are a bunch of them. There are fields of the animal interface: name, owner name, and friends. There are fields in the under the specific type for the dog or for the cat or bird. In our case, the dog fields need to be included into the collection. So the GraphQL engine collects all fields that are relevant to the dog type returned in the previous query in the animal field, and they are name, owner name, breed, barks, friends. And then it needs to perform the same operation again. It needs to resolve the fields. So some of the fields are resolved against with using the result produced by the previous query, but some of the fields, in our case, friends, need to again query the friends data source, and imagine that the friends data source returns back a list of friends. And the next step in the execution will be to collect the fields for the in the friends selection set, and in this case they are name, dog name. I'm sorry, name is dog owner, is cat owner, or is bird owner, and resolve them. So the query engine collects all the fields and then resolves all the fields. And I would also point that it will invoke this resolution or resolvers as many times as many elements were returned in the friends list by the friends resolver. So this is the just illustration of the standard GraphQL query execution as it is described in the spec. So as you see, during that process, the engine performs a lot of redundant work. It needs to collect the fields, it needs to merge the fields, it needs to resolve types. And in case the same query or the same query type, I would say, is received by the server multiple times, that becomes even more relevant because every time the engine would do the same redundant work over and over again. It also, when we walk through the GraphQL query execution, one could notice that there is a specific order in the GraphQL in the query execution. The children fields need to be executed after their parents. So the execution or resolution of the children fields depends on the resolution of the query field. So this all makes it possible to separate the query analysis from the query execution. And the query analysis, where we collect the fields, detect the fields that need to be executed, when we could be recorded into the graph. In our case, it is and the best suitable case would be the directed acyclic graph or dependency graph, if you will. And as you see, each merged and collected field could be represented in the graph as the vertex. For the fields that have the abstract type, like in our case, the animal field, we can also, and we should, in order to continue with the field discovery, we should detect all possible very concrete variants of that abstract type and to record them into the graph. And these vertices are indicated on the graph with a slightly different color, with the green color, to represent the special vertices that are concrete that are associated with the types that are concrete types of the animal interface. So the relationship or the dependencies between parent fields and the children fields are recorded as edges. So as you see in the query selection set, there was an animal field and there is an edge between the query and the animal vertex. For the for the doc type, there are fields name, owner name, barks, breed, and friends. They are also recorded into the as edges into this graph. So each edge represents a possible parent-child dependency relationship between the fields. So why it is important? First of all, we could say that execution of the GraphQL query is a process of enumerating the edges between the vertices and then executing the field resolver or actions, if you will, associated with the edges according to that order. In order to collect the or build the sequence of edges, the graph structure allows us to first topologically sort the vertices, and topological order means that the vertices with the least dependencies appear in the sequence before the vertices with the most dependencies. So this way you can see that the least dependent field or least dependent vertex that represents the topmost selection set query appears first in the sequence. And for instance, the field like is doc owner, is cat owner, that depend on their parent field friends, the corresponding vertices are represented in this sequence at the end of the sequence. So this is the first step in building the sequence of edges. From after enumerating the vertices, we can find all the incoming edges into each vertex, and we can group those edges into the separate buckets in order to collect the edges that could be resolved independently. And this table represents the buckets of the independently resolvable edges from left to right. First, we start with edge 0 to 1. That's the edge between the query and animal vertices. The next bucket would be the edges between animal and animal dog, animal cat, and animal bird vertices. The next bucket would be the all edges that are outgoing from the vertices animal dog, animal cat, and animal bird. And the last bucket will be all edges outgoing from the vertex friend. You also can notice here that some of the edges are painted in red, and the corresponding elements in the tables are also painted in red. These edges, while they still exist in the query plan or in the graph, these edges are executed. They are not executed during this particular kind of query, because the graph represents the statically result of the static analysis of the query. Not all of the paths in the graph get executed at the runtime, and they depend on the actual data. In our case, the actual data during the graph query resolution was the animal of type dog, and therefore all edges that are related to other concrete types like cat or bird, they are not executed in this case. And it is also worth mentioning that as we evaluate the query plan, each vertex in the plan is associated with its own data. We accumulate the data for each vertex, and they need to be separated from each other because the query plan is reusable across multiple queries, multiple requests with the same query type. Whereas the data for each vertex is request specific. That's why for each request, we need to create an instance of the query plan data store where we can keep track of the accumulated data for that particular request. So this is mostly, you can represent that as a map with the key, the vertex ID or the vertex, and the value for each entry would be the accumulated data for that vertex. So then let's see what the key components of the static query analysis should be built into the query plan. First component is the merging fields. Imagine that we have the query with the fields repeated in multiple places, with the same field repeated in multiple places. Like, for instance, the field name. There is a field name under the animal selection set. Then there is field name under the cat fragment. Then we have this field name under the dog fragment. Similarly, the field friends we have under the cat fragment. We have the field friends listed twice under the bird fragment. This is allowed by the spec, and when the this spec defined algorithms demands that these need to be discovered and merged at the time of the execution. With the query plan, we don't have to do this. We can do this once when we build the query plan, and each field merges to the field, the same field with the same name and label under the same type condition, and that merged field is represented as a separate vertex in the query plan. So to be more specific, or to be mostly correct, we can say that each vertex in the query plan is not one single field as it is described in the query. In the query, it is actually a merged field obtained by merging the fields of the same with the same name under the same type condition, and that creates the vertex. And again, after we create the after we build the set of vertices, we can build a set of edges. And in this particular case, for this particular query, the only executable set of edges would be in the first bucket 0 to 1. That is resolving the field animal to Toby. We know that Toby was a dog. And then resolving the age 1 to 5, because in this case, age 1 to 5 acts like a filter, selecting from the set of animals returned in the previous step into the vertex data, the vertex 5 data, only the dogs, and then executing the age 5.2 that produces the dog's name. So the result would be just result of executing this path. With the result would be the name of the dog that was created. The next component that need to be considered when we build the query plan is the abstract fields. Abstract fields, again, those fields that have the type of interface or a union. And in order to do the static analysis of the query, we need to provide a record in the plan all possible variants for that interface of the query. Hopefully, they are known from the. Fortunately, they are known from the schema. In our schema, the animal interface has 3 concrete types: dog, bird, and cat. In case of unions, all components of the unions are also known. So the plan should contain all possible cases of the concrete type in order to not to make these decisions at the runtime. The third component is the conditional fields. The conditional fields are fields that have directives include or skip. In this case, I place the directive include if directive has value true, the field is included. If the field has the value false, it is excluded. And these conditional conditions represent the edges that should be conditionally either evaluated or conditionally skipped during the execution. In case of the static bindings, like this one, the edges that should be excluded from the plan, they could or even not be recorded in the plan at all. But in some cases where the argument values for the include or skip directives are provided via variables, it is better to record these edges as they are, and then evaluate them on the at the runtime, depending on the actual value of the arguments. One of the interesting consequences of having query plan is a different way of realization of the execution strategy for the mutations. The spec demands that mutation fields need to be executed sequentially. And for that, GraphQL Java, for instance, has a separate execution strategy that ensures that the mutation fields are executed one after another in the order they are provided in the query. And then after the mutation fields are resolved, the results of those, that's a query part of the mutation, they could be resolved using the standard execution strategy that just provides a synchronous resolution of the fields. With the query plan, it is not necessary because we can control with the query plan the execution sequence by providing additional edges between fields. These edges need not be actionable, but just having the edge between, in our case, we have the mutation fields add doc and add cat. Add doc is labeled as Labrador, add cat is labeled as Sphinx. And in order to ensure that the field Sphinx is resolved after the field Labrador, we just need to provide an edge between the field Labrador and Sphinx, and presence of this edge will ensure that the field or vertex Sphinx will be placed in the topological sequence after the Labrador, and therefore the resolution, the field resolver for the Sphinx will be executed after the field resolver for the Labrador. So just like in our case, the first edge to resolve will be 0, 1, 0, the add animals, that's the topmost query selection set to Labrador. The next one would be Labrador to name, and animals to Sphinx, and Labrador to Sphinx. And Labrador to Sphinx, that's not actionable edge. It is placed here just to ensure the order of the operations. It doesn't have to, it doesn't produce anything. But the effect would be that the H0 to 3 that invokes the resolver for the field Sphinx will be executed after the H0 to 1 that invokes the resolver for the field Labrador. One of the important tasks to when executing the GraphQL query is to perform the query cross analysis. Query cross analysis is important to prevent the very complex queries from execution, because they can either destroy the system or by producing some sort of DDoS attack, or they can take too long time to execute, and the client will not be satisfied with the results. So therefore, it is important to be able to upfront somehow estimate how costly the query is. And in many cases, there are separate systems or there are separate components in the GraphQL engines that calculate the query cost analysis, simply because the GraphQL spec does not provide any mechanism for the query cost analysis based on the query execution. With the query plan, as you see, the cost analysis could be performed over the same query plan, and it is, again, it consists of the same steps as if we executed the query. The only difference is that during the query, during the cost analysis, all we need to do is to obtain the cost of evaluating of a particular edge. Each edge could be associated with the cost, versus in the case of the query execution, each edge is associated with the field resolver that obtains data. So in the query cost analysis, we use exactly the same standard mechanism. We're working with the same source, which is query plan, and that makes it very accurate comparing to other methods, because the other methods could go easily out of sync with the actual query execution. So in our case, again, I will not walk through the way how the query is executed, but just to notice that the age 0 to 1 is calculated based on the most of the costs for the actual types, because the animal type is the abstract, and we have the cost associated with resolving to bird, cat, or dog, and the cost of this resolution is the highest cost of the associated with the type that is derived from the animal. And also the third bucket of the edges, where the edges are resolved in parallel. When you resolve the edges in parallel, the cost is calculated as the cost of the highest cost of the edge in that bucket. In our case, in that bucket, we have the edge. We have edge 2 or 3 or 4 to France, and resolving to France, that's the 212, 312, and 412, and the cost of evaluating to France is 10, and therefore the whole bucket evaluates costs the 10 points, and therefore the total cost of such query is 16 points. What else could be done is with the query plan. That's already beyond the spec. Imagine the situation where we need to evaluate some fields or resolve some fields only after the other fields of the same type have been evaluated. And it doesn't matter to make them, it doesn't make sense to make that field dependent on in the different selection set. It belongs to the same parent type, but it needs to be evaluated after the other fields. For instance, in this case, this is imaginary situation, but it would be very easy implemented. Imagine that I want to add a field isPet owner to my friend type, and the isPet owner is a calculated field. It is not the field that is fetched from the data source, but it is calculated based on the expression provided in the eval directive, and it evaluated to true in case this friend is dog owner or it is a cat owner. In this case, after parsing the expression, the parser can figure out that in order to resolve the field is pet owner, the fields is cat owner or is dog owner have to be resolved first. And that goes against the spec, because in the spec, the fields that on the same level under the same parent or are in the same selection set. need to be executed in parallel. So we need to somehow make fields is doc owner and is cat owner executed before the field is pet owner. And in order to do that, we can record additional dependencies in the query plan between the vertices or fields is doc owner and is pet owner, is cat owner and is pet owner. They are indicated with different color on the plan, and that will ensure that the field is pet owner will appear in the topological sequence after the field is doc owner and is cat owner, and therefore the incoming edge for is pet owner that would which is 1 to 6 that would invoke the resolver for that field could be bucketed in the different bucket after the edges that resolve the is doc owner and is bird owner. Another interesting case or advantage of using query plan is optimizing the query execution. Imagine that we have the field under the animal type field friends. This query asks for the friends, and friends field depends only on the foreign key, on the name of the animal, and the name of the animal is already provided as the argument to the animal field. So therefore, just like in the previous example, in normally the field friends would be executed or resolved after the field animal is resolved, and that would produce the cost 16, as we saw during the query cost analysis slide, that it would produce the cost 16 for this query. But we can do smarter than that. We can create a new vertex in the plan that represents that would contain or would be associated with the data for the friends of animal with name black, and that could be recorded in the plan in such a way that we create the edge between we can place basically it in the same selection set as the animal field. We can create the edge between the topmost selection set query with that field, and that edge will guarantee or will place will be executed in parallel with execution of the field animal. And imagine that we can associate that edge with the function that resolves that goes against the friends data source and reads all friends of the animal friend, or of the animal black, I'm sorry. So that edge will be executed in parallel with the edge 0 to 1, which resolves the animal itself. So by the time when the execution comes to the edge C12 that should return all the friends for the animal, the data for those friends have been already executed in the previous step. So the resolver for the edge C12 could simply go and fetch the data that was prefetched before, and that drastically simplifies the query or makes it executed faster. Because take a look at the resolution order. So the first edges to resolve would be edges 0 to 1 and 0 to 17, and we know that the cost of the edge 0 to 1 was the highest cost of the resolving one of the animal types, which was 6, but the 0 to 17 cost would be 10. So in this case, the overall cost of this step would be just 10. And then on the third bucket, in the third bucket, where the age 3 to 12 need to be executed, in that case, the age 3 to 12, instead of going and the resolver for that age, instead of going against the friend's data source, it will just get the friends from the cache because it was already fetched, and that costs nothing, and therefore the overall total cost for this query would be just 10 instead of 16 as it was in previous case. Just translate this cost to the milliseconds. Imagine that each point is actually, let's say, 100 milliseconds, and then you can easily see that instead of 1600 milliseconds, the execution of such query can go to just 1000 milliseconds. And with the query plan, we can do more, much more, and we plan to build that. I don't have the slides to show that. I can just simply describe what else could be done with the query plan. Complex criteria query. This is usually quite helpful when you need to orchestrate over a set of the various independent data sources, and the criteria might contain the query criteria might contain the filters against various data sources, and in order and therefore we can decompose that criteria, and we can schedule the execution of the queries applying the filters against various data sources and still use the same query plan with the same topological and edge sequence to produce the result. Cascade mutations is kind of similar in case we want to have create a mutation of the object across multiple data sources, where some fields belong to one data source, some fields belong to another data source. We can also decompose that object onto the set of smaller objects and execute the smaller mutations across particular data sources, and then produce the results. And again, the query plan is suitable to do this because the fundamental mechanism how to execute queries doesn't change. It all depends on how we record the vertices and edges into the plan. Another thought that we want to explore would be detecting and optimizing outlier fields. That means that we can shuffle around fields in the plan by introducing additional intermediate vertices and edges in such a way that we can place the edges that cost most in the different buckets, where the impact of that cost will be compared to the impact of the other edges in the same buckets. So this we sort of saw that when we discussed the prefetched field analysis, but there could be more complex scenarios where this could be useful. We need to add subscription support based on the query plan, and subscriptions are also a good example of value of the query plan, because we will build the query plan only once and only execute it with every data change in order to produce the notifications instead of evaluating the same query over and over again as the data get changed. And also we can provide the different stream support, directive support. They are not parts of the GraphQL spec yet, but they are coming soon, and that also could be quite easily built using a query plan. So that would be the last slide in my talk, and thank you very much for listening. In case you need to contact me, this is my email and GitHub handle, Twitter and LinkedIn. Please feel free to reach me out, and I will be happy to help you or answer to your questions. Thank you.